Math 230, Quest to College. I'm Joe Vasta, and this is our first official mathy lecture for this class. We're going to look at topology and Fibonacci numbers. Before we get started, here's a little puzzle here which you could choose to skip if you want. There's n chairs in a row. How many ways can you seat boys and girls in these chairs so that no two girls sit next to each other? So this is kind of a weird puzzle. The way I would start it off is if you had one chair, n equals 1. Well, if there's just one chair, you can sit a boy in that one chair, or you can sit or seat a girl in that one chair. So when n equals 1, there's two ways. When n equals 2, that means there's two chairs. You can sit boy, boy, there's one way. Maybe I'll put commas between these. You can do boy here and a girl there. You could do put a girl there and a boy there. And then normally we would say, oh, then we can go girl, girl. But the stipulation is no two girls sit next to each other. So we can't have girl, girl. There are three ways. So we go with 3 chairs. And with 3 chairs we have boy, boy, boy. And then you have some other possibilities, but you can't have the possibility girl, 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 or girl, girl, boy. No two girls sit next to each other. So the deal is there some sort of pattern here with our answers as we continue to add extra chairs? Now, in terms of this class, you could say, I don't care about this problem, and that's all right. I'll come back to this problem at the end. Some of you may want to see if you can figure out the answers for the next 4 or 5 configurations, and we'll see how you do on that. Okay, so math is pretty complicated. It has lots of different branches. What I'm presenting right here is just 20 branches. There's a lot more branches to math than what you see here. We have the algebra, geometry, trigonometry, calculus, and that's usually what you see early on. But if you go to the university, you'll see that they teach such topics as set theory, logic, number theory, graph theory, combinatorics, probability. Maybe you've seen that in a statistics class. Real analysis, complex analysis, numerical analysis, topology, abstract algebra, linear algebra, differential equation. We actually teach that here at Quest, those two. Chaos theory, game theory, cryptography. The list goes on and on. So in this math class, we're actually going to be looking at some of these other topics. The one that I want to focus in on is topology. Okay, so we'll take a few minutes to talk a little about topology, just to show you that math isn't always solving for X. There's a lot more excitement in math, and unfortunately the way our education is, we push the algebra and geometry pretty heavy in high school. So much so that lots of people who probably would have been good at some of these other ones say, I don't want to get a technical degree. So let's take a look at topology and see what's up with topology. Okay, so in the kindergarten, so I'm going to go all the way back to kindergarten to have this discussion. We learned about squares. Okay, and we said, oh, that's a square, and then that's a circle. And if we said, hey, that's a circle and that's a square, we got them switched up, they would slap us, or what, depending on how mean your kindergarten teacher was. So we were told that those are different things, and they are. But in topology, the square equals the circle. So what is that all about? Well, a topologist, that's somebody who studies topology, will look at this square as, think of this as a loop of string. So that loop of string can be stretched or, rearranged so it becomes a circle. So topologists are all about stretching, bending, shrinking things and calling them equivalent. So they'll say a square equals a circle, or they'll use the word a square is homeomorphic to a circle, which also means that these guys equal a triangle, but I'm not going to draw that. They actually equal this right here, which is a little circle. So it's pretty weird when you see topology for the first time. But this is pretty much the beginnings of a whole topic of math, called topology. And I'm going to give you your first quiz. Really, you don't have to worry about this. I'm not going to grade it or anything. Which two figures are equal or homeomorphic? So we have that. 1, 2, and 3. Two of these guys can be distorted to the other. Okay, so you can take one of these and distort it to the other one. So you could pause the video if you'd like. Maybe you want to think about this. And if you really don't care about topology, then just keep it running. We're almost done talking about topology. Okay, so I'm going to go ahead and tell you the answer, and maybe you've already figured it out. Figure 1 and figure 3 are homeomorphic. Now, how did we get that? And some of you would be able to tell me. Here's figure 1, and here's figure 3. What we did is we turned this circle into a square. So think of this maybe as a string. Maybe some strings are attached. We turn this stick figure person upside down, took this part where the neck is, and we flipped the body inside the square. And then we made the arms a little longer, and then the legs did the splits and got a little shorter. So figure 1, which was this guy, and figure 3 are homeomorphic. Now, if you're getting a little worried saying, wow, I'm going to have to do this stuff on the exam. No, there are some things in this class that we throw in there just to make your math class interesting. In an algebra class, probably they've already started solving equations in their lecture videos. Oh, how fun would that be? But in this class, we're going to do more interesting things. So you can do this twisting, stretching, turning in 2 dimensions. This is 2 dimensions. But you could also do this in higher dimensions. And so here's a very famous thing in topology where a donut becomes a coffee cup. So this donut gets distorted to this. So think of it maybe as a piece of clay. And it has that hole in it. And look, track the hole. The hole becomes the handle. Now in topology, they wouldn't call that a hole in the torus. This is called a torus in topology. But because we're not experts at it at this level, I'll just say that's the hole, and it becomes the handle of the coffee cup. And those two shapes, the donut and the coffee cup, are essentially the same to a topologist. Now, a branch of topology that wasn't on our list of 20, so sometimes these topics will have branches within themselves, is called knot theory. And in knot theory, they study knots. Now, this could help with things like DNA analysis, etc. So what I'm going to leave you with, and this is the disadvantage of not having face-to-face class, because we could actually do this in front of the class with a few volunteers, is this little trick here. So if you've got some friends, you could take the ring from the string. You have a loop of string, and it's around 2 fingers there. And this kind of goes through the steps. I know I'm not an artist here, of how you could take this ring off the string without removing the string from the fingers. And so, it looks pretty complicated, but when you have this all set up, you let go of the string and take the ring. Of course, this is not going to be a problem on your exam, but this is just introducing you to a branch of math that we usually don't study in high school or even before high school, and the branch is called topology. This part is knot theory. So that's the deal. So everything that I've done so far, topology, is really not going to be covered on the test, and it's just something for you to think about, like, wow, math could have been funner in our other classes. So now we're going to take you to the next topic that we're going to cover, which is sequences. And this is actually going to start a little 1.1, but I'm not going to put 1.1 there. I'm going to write out this right here. Sequence. So sequence, what is that? That's the fancy word for list. So a sequence is a list. Now in the math world, we like to say that's a list of numbers. But it really doesn't have to be numbers. A sequence of colors, a sequence of letters, etc. So what we're going to look at is this one guy from history. His name was Leonardo. We'll try to make this easy with his name because his name does have a little story behind it. Leonardo Fibonacci, and he was born in 1175 AD, and he lived to died in 1250. He was born in Pisa. He traveled widely. He advocated the use of the Hindu-Arabic decimal system, those are our numbers, over Roman numerals, and so he helped Europe go away from the Roman numerals because they were so inefficient in terms of calculations. So Fibonacci has a rabbit problem that he posed. And so let's talk about Fibonacci's rabbit problem. Okay. A single pair of baby rabbits is placed on an island. Each adult pair gives birth to a new pair every month. So I take it these pair of baby rabbits, one was a male, one was a female. Each pair reproduces from the second month on, and no rabbit dies. Obviously, Fibonacci wasn't really thinking about true biology because there's a lot of assumptions here. But let's just go with this. How many rabbits would you have at the beginning of each month? That's the question. So what I'm going to do is I need a whole nother piece of paper to actually illustrate this. So here it goes. So the beginning of month 1, we have pair of baby rabbits. From time to time, sometimes I will stand up and look in the camera to see if things are still working. So we have, at the beginning of month 1, how many pairs? There's 2 rabbits there, but there's 1 pair of rabbits. So what's going to happen? Well, after a month, those rabbits, the male and the female there, they grow up and become adults. So at the beginning of month 2, you still have 1 pair of rabbits. Okay, so now this is when things get interesting. At the beginning of month 3, these rabbits are going to have a pair of babies. And so at the beginning of month 3, you have how many pairs? Here's a pair, 1. Here's a pair, 2. So beginning of month 3, 2 pairs. Okay, beginning of month 4. These guys are still going to have another pair of rabbits. So that is what we're going to do. So this is now the beginning of month 4. They have another pair. And at the same time, these guys right here grow up and become adults. So at the beginning of month 4, we have 3 pairs. Okay, beginning of month 5, what's going to happen? Each of these pairs are going to produce another pair of baby rabbits. So a pair of baby rabbits, a pair of baby rabbits. So let's go ahead. So these guys, I'll just put them right here, that baby pair, and then these guys here have this baby pair. And at the beginning of month 5, these ones have grown up into adults. So how many pairs do we have? 1, 2, 3, 4, 5. Okay, beginning of month 6. So how many new baby pairs am I going to put? 1, 2, 3. So we'll do that. 1, 2. This is really high tech, isn't it? Double stick tape and paper. So it's not too late to try to switch to another Math 230 section where probably they're doing this on PowerPoint. 3 baby pairs from those, and then what happens to these ones? Well, they become adults. And so let's count the pairs of rabbits that we have. 1, 2, 3, 4, 5, 6, 7, 8. Let's walk this out just maybe another time here. So month 7, beginning of month 7, I'm going to put how many baby pairs? I'm going to put 5 baby pairs. Hopefully I have enough of these. 1, 2, 3, 4, 5, and then at the beginning of month 7, these guys all grow up to become adults now. So if we count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. The numbers that you see right here, that's a list of numbers, so it's a sequence. And this sequence here that I have underlined in orange is the Fibonacci sequence. And so you might say, well, what happens at the beginning of month 8? Well, I've run out of paper for this. So we got to think of another way of getting the number that goes right here. And maybe a way of thinking about that is seeing if there's a pattern. So you might want to, if you've never seen this before, pause the video and see if you can see a pattern, maybe a pattern that would generate the next Fibonacci number. These are called Fibonacci numbers. Okay, so maybe you did it, maybe you didn't. What pattern you might see is this. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. So to get this one, you go 8 plus 13, and this gives you 21. So we can keep generating this sequence. It has infinitely many numbers in it. They get big. The next one then would be adding those two together, which would give you 34. And then you might have 55, 89. I'll list them off on the next piece of paper. So this little story about rabbits that Fibonacci told gave us the Fibonacci sequence. Sometimes we just call these the Fibonacci numbers, and it seems like kind of like a dumb thing. It seems like people were really bored and they just thought of, well, there was no TV back then, for one thing, and they just thought of silly problems. But let's take a look at these Fibonacci numbers, and you actually find them in more places than you would think. Okay, so here is the sequence that we had, 1, 1, 2, 3, etc. And they go pretty high. I mean, they continue. The next one, I believe, is like 144. And so you could Google this and get a lot more information about this. But the Fibonacci numbers are seen in nature. If you count the number of petals on certain flowers, the mature flowers, you'll count lots of times Fibonacci numbers. So I read that lilies and irises have 3 petals. There's a 3 there. Buttercups usually have 5 petals. The marigolds have 13. Daisies usually have 21, 34, 55, or 89. So you can look this up on the internet, and maybe you're like, this guy's going crazy, but that's true. So that's number 1. Number 2, leaf arrangements in certain plants will go by these Fibonacci numbers. Number 3, number of spirals on pine cones, pineapples, sunflowers, on mature pineapples and mature pine cones and mature sunflowers. And so maybe next time you're at the grocery store, you can pick up a pineapple and count the spirals, or not, because in these times people look at you funny if you touch fruit and then put it back for some reason. Everybody wearing masks. Some people even wearing gloves. So maybe you should just buy one and count the spirals. I actually have a pine cone right here. It's not a pineapple, but it's a pine cone. We'll see how it... Oh yeah, there it is. So I'm going to count the spirals on this pine cone. And I'm going to start off, it's hard to see in the video, but I'm just going to go ahead and count them. I know you're probably thinking I'm going to cheat and go 1, 2, 3, 4, 89. But here it goes. 1, 2, 3, 4, 5, 6, 7, 8. And I started by counting that one. I counted 8 spirals. I'm going to count the spirals the other way, okay? So the spirals actually go both ways, and so when I do that, I have 1, I'm looking at that black mark right there, 2, 3, 4, 5, and I'm back to that one again. So I counted spirals one way, I got 8. I counted them the other way, I got 5. Piano scales. Okay, so if you play the piano, you know about octaves. An octave is like going from middle C to the next C. 1 octave on the piano contains 2 black keys together, then 3 black keys together. For a total of 5 black keys together, there are 8 white keys, making a total of 13 keys when you are playing an octave. Starting at C and going to the next C, you have touched 13 keys. The bee colony is another example. So the bee colony has some characters. It has the queen, workers, those are females who produce no eggs, and drones, males who do not work. Females are produced by a male and the queen, so a female will have two parents, and a male, which is produced by the queen's unfertilized eggs, will have only one parent, which is just the queen. So if you look at the genealogy of the male bee, it would look like this. So I wrote it out here. So here's the male bee. It just has a mom, and then she, since she's female, has both female and male. Okay, so this is the parent, this is the grandparents. There's only two grandparents really, and then there's three great-grandparents of this male bee, because this male only has a mom and this female has two parents. And so we keep going up, and we have a few generations, 1, 2, 3, 4, 5, 6 generations. Well, take a look at what we have here. The Fibonacci numbers are screaming out at you here on this, because in this first generation, this first level, there's 1. In the second generation, or maybe let's say the next generation up, there's 1. And then this generation, grandparents, there are 2. Great-grandparents, there are 3 on that level. And 1, 2, 3, 4, 5 for that generation. And then 1, 2, 3, 4, 5, 6, 7, 8 for that generation. And we ran out of paper here, ran out of room on the paper. But if we continued up, the next generation would have 13, which is our next Fibonacci number. Okay, let's take a look at a few other things with Fibonacci numbers. So sometimes what math people will do is they'll take something that's interesting like Fibonacci numbers and make it more complicated, and they call the first Fibonacci number F, and that's a subscript. So F sub 1, or sometimes we say F1, and F2, and F3. So 21, you could pause the video and think about what that would be. Okay, 21 happens to be, let's count them, F1, 2, 3, 4, 5, 6, 7, 8. 21 is F8. Now, 21 is gotten by adding the 2 previous Fibonacci numbers. So F8 actually equals F7 plus F6. So in the Fibonacci world, they have a formula called a recursive formula. So, I mean, some of you might start losing it here, and that's all right. You're not going to be tested on this. Fn, the nth Fibonacci number, is gotten by going Fn minus 1 plus Fn minus 2. This right here is called the recursive formula. And if you have a recursive formula, they usually have to give the first 2 or the first few terms of the sequence. So F1 is 1, F2 is 1. These are like your stepping stones to get you to F3. And then you use F3 as a stepping stone to get to F4. And so there's the formula. The problem with this formula, so this is called a recursive formula. It's a great formula, but the problem is if you want the 100th Fibonacci number, you've got to write the first 99 Fibonacci numbers so you can then compute the 100th. So is there an explicit formula for the Fibonacci numbers? And the answer is yes. So the explicit formula will give us whatever Fibonacci number we want. So here it goes. F sub n equals 1 over the square root of 5, 1 plus root 5 over 2 to the nth power minus 1 over root 5, 1 minus root 5 over 2 to the nth power. You don't have to memorize this or even use this. This is the explicit formula for the Fibonacci numbers. So what does this mean? Well, there's square root of 5s in there, so that looks pretty scary. But whenever you put a natural number in here, like 1 in for n, you put 1 in for n. We're not going to do this now. But the algebra will make it so all the square root of 5s cancel. So f1, when you put 1 into the right-hand side of this formula, you will get 1. And when you put 2 in for n, there's going to be more algebra. And when all the dust is settled, you get 1. You put 3 into the formula, this thing will eventually, when it's all simplified, give you exactly 2. You put 8 into the formula. No one would want to do that by hand. But if you put 8 into this formula, when all the algebra is done, you would get 21. So it's kind of an ugly formula, but on the other hand, it's weird how all the square root of 5s go away when you put a natural number in there. The other thing about Fibonacci numbers that I didn't want to get into was their connection to something called the golden ratio, which is 1 plus root 5 over 2, and this is by taking ratios of Fibonacci numbers. There's Fibonacci spirals and shells, and we can keep talking about the Fibonacci numbers, but I think some of you have probably already had enough of that. So let's go ahead and get back to the question that we started doing at the beginning of this video about the chairs. And so look what we have. So I'm coming back to this one here. Let's go ahead and write out some more methods, maybe some more configurations. Maybe you have figured this out on your own and you're looking at your answers and you're now, something's clicking. But let's just do this. Boy, boy, boy. So you can have boy, boy, girl. So I'll do the ones where there are 2 boys exactly. Boy, girl, boy. And girl, boy, boy. Now when we only have 1 boy, you can't have girl, girl, boy because no 2 girls sit next to each other. So the only way with 1 boy is to put the boy in between the girls. Okay, that's the only way you can have 1 boy, and then you can't have the configuration of no boys because then all 3 girls would be sitting next to each other. So let's see, 1, 2, 3, 4, 5. 5 ways. Let's go ahead and look at n equals 4. And so we can have boy, 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 boy. Now this is just like a little puzzle. If you've had enough of this, then you can skip past this part. Then you can have 3 boys. So you can have boy, 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 girl, boy, boy, girl, boy, boy, girl, boy, boy, and girl, boy, boy, boy. Now you can have 2 boys. So you don't want boy, boy, girl, girl, but you can have boy, girl, boy, girl. And you can also have girl, boy, girl, boy. And the only other way you can have 2 boys exactly is to go put them, oh wait. Searching for something, but oh well, I can't find it. Let's just cross that out. So the only other way you can do this is to go girl, boy, boy, girl. I don't think there's any other way you can have 2 boys and sit these people so no 2 girls sit next to each other. 3 girls, there's no way you can do that with this rule here, and 4 girls, no. So let's count this. 1, 2, 3, 4, 5, 6, 7, 8. 8 ways. Now, before we do n equals 5, let's take a look at our answers. We have 2, 3, 5, 8. Do those numbers look familiar? Well, they should. Those are the Fibonacci numbers. So when n equals 5, instead of writing it all out, we would then say 5 plus 8, which is 13 ways. So the answer to this puzzle, really, there are n chairs in a row. So when you just have n, let's see, if you were looking at n equals 5, which is 13 ways, 1, 2, 3, 4, 5, 6. That's our 7th Fibonacci number. So this would be f n plus 2. Okay, now if that's confusing, don't write it down. But there it is. So if you have n chairs, then the number of ways that you can do this is f sub n plus 2. So because this right here is the 3rd Fibonacci number when n is 1, and this is the 4th Fibonacci when n is 2. Okay, so that pretty much ends this lecture on topology and Fibonacci numbers. Each time I do a lecture from now on, I'll have a video link, and then right next to the video link it will say PDF, and that will have a PDF of the stuff that I have written out here. So hopefully that will be very clear, and then you could even print out the PDF, you know, on future lectures first before you watch the video, and then you can kind of see what I'm going to be doing in the video, or whatever, however you want to do it. But this ends it. Now in terms of the homework, we got just a tiny bit into section 1.1. After this lecture, I wouldn't do any homework. Do not do any homework on what we just covered. The homework part of this class will start on the next lecture when we officially do 1.1, and we'll be looking for patterns of sequences. So let me get this clear for you guys. There's no homework on what we've been covering. What we've been covering is sort of an introduction to the sort of crazy math that we will experience in this class. Well, you guys have a good day, and I'll see you next time.